In this video, we're going to look at the final type of a non-homogeneous second order differential equation. So let's start off by solving the auxiliary equation, which is going to be m squared minus 5m plus 6 equals 0. And we've done this in previous videos. So therefore we get m equals 3 or m equals 2. So our complementary function is going to be y equals to a e to the power 3x plus b e to the power 2x. So if we were to follow what our particular integral would be, as in we've got something in the form of e to the kx, our particular integral would be y equals c e to the kx. Now the issue with this is when we differentiate it, first derivative and second derivative, and substitute it into our equation, we would get 0, and we can't have that. So let me show you how. So if we were to assume that pi is going to be y equals c e to the kx, and we differentiate that. So dy by dx is going to be, so in our case it's going to be a 2 there, so we put a 2 there. So it's going to be 2c e to the 2x d2y by dx squared would be 4c e to the 2x. Now when we substitute it into our differential equation, this is what happens. So we're going to get 4c e to the 2x minus 5 times dy by dx plus 6 times the particular integral is equal to e to the 2x. Now what happens is we get 4c e to the 2x minus 10c e to the 2x plus 6c e to the 2x equals e to the 2x. But then what we have is e to the 2x equals 0. Well, we know that can't happen because e to the 2x is always greater than 0. So this is a scenario that we can't afford to happen. And also, if we notice that because our particular integral is a constant times e to the 2x, we've already got that already in our complementary function where we've got b times e to the 2x. So we're not allowed to have that. So we need to change our particular integral by multiplying it by x. So now we would assume that pi is now going to be y, and here's the important part, we cx e to the 2x in our case. So then when we differentiate this, we would have to use the product rule. So that's going to be cx times e to the 2x differentiated plus e to the 2x times cx differentiated. So that's going to give me 2cx e to the 2x and then plus c e to the 2x. Now we need to differentiate this again for the second time, so we use the product rule again. So it's going to be 2cx multiplied by 2x differentiated plus e to the 2x times 2cx differentiated, and I'm just going to just differentiate the last term on its own, plus 2c e to the 2x. So that will now give me 4cx e to the 2x, and that will give me plus 2c e to the 2x plus, I'll write it in pink here, plus 2c e to the 2x. And what I would end up is I will get 4cx e to the 2x plus 4c e to the 2x. So now we're going to substitute these into our differential equation. So we get 4cx e to the 2x plus 4c e to the 2x minus 5 times dy by dx. So let's put that in. So we get 2cx e to the 2x plus c e to the 2x plus 6 times the particular integral, which will be cx e to the 2x. So now we're going to simplify this down. So we're going to get 4cx e to the 2x. And don't forget, all of that must be equal to e to the 2x. So we get 4cx e to the 2x plus 4c e to the 2x. Now, being consistent here, using pink, minus 10cx e to the 2x minus 5c e to the 2x. And then we've got plus 6cx e to the 2x here. And all of that is equal to e to the 2x. So what we end up with is the following. Is we're going to get 4cx e to the 2x minus 10cx e to the 2x is minus 6x e to the 2x plus 6cx to the 2x will cancel out. So they're just going to cancel out here. So I can just cancel those out here. There you go. And I get 4c e to the 2x minus 5c e to the 2x is minus c e to the 2x is equal to e to the 2x. In other words, minus c is equal to 1. Therefore, c is equal to minus 1. So my particular integral would be y equals cx e to the 2x. So in our case, it's minus 1x e to the 2x. So we can say that the general solution is y equals to the complementary function plus particular integral. So in our case, it's going to be y is a times e to the 3x plus b times e to the 2x, and then for consistency, writing that particular integral in pink, minus 1x e to the 2x is our general solution of the second order differential equation. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So the first thing we ought to do is solve the auxiliary equation. So we get a nice repeated root here. So m equals 1 or m equals 1. So don't forget, I've done videos on this. So we'll get this a plus bx times e to the power of x. So the issue we have in this problem is that the complementary function contains a times e to the x, and it also contains a constant b times x e to the x. So we can't use any of them as our particular integral. So what we have to do is to multiply x e to the x by another x, which implies that we're going to assume that our particular integral will be as follows. So we assume that the particular integral is going to be y is c x squared times e to the x. Now what happens is we're going to differentiate this by the product rule. So we're going to say dy by dx is cx squared times the differentiation of e to the x plus e to the x times the differentiation of cx squared differentiated, which implies I get cx squared e to the x plus 2cx e to the x. Now, doing the second derivative, again I have to use the product rule quite a bit here, so it's going to be cx squared e to the x differentiated plus e to the x times cx squared differentiated. Then I'll do the other one here, so it's plus 2c x times e to the x differentiated, like so. So, include the clarity of my handwriting, plus e to the x times 2cx differentiated. So we've got to be careful with the differentiation here. So what we end up with is we're going to get cx squared e to the x plus 2cx e to the x. And then we're going to get plus 2cx e to the x. And then we're going to get plus 2c e to the x. Therefore, this simplifies to be cx squared e to the x plus 4 lots of cx e to the x plus 2c e to the x. Now we're going to substitute this into our differential equation. So we get cx squared e to the x plus 4 times cx e to the x plus 2c e to the x, and then we have minus 2 times dy by dx. So let's write that in. So it's minus 2 times all of dy by dx. So let's write dy by dx in. So we're going to have cx squared, like so, e to the x plus 2cx e to the x as follows. And then we also have plus y, so that's going to be our particular integral, which we said was going to be cx squared e to the x. So I can do that in orange here. So plus cx squared e to the x. Now all of that is equal to what we have on the right hand side of our differential equation, which is e to the x. So what we end up with is cx squared e to the x plus 4cx e to the x plus 2c e to the x. Then in pink here we get minus 2cx squared e to the x minus 4cx e to the x, and then in orange plus cx squared e to the x. I'm going to write that on the next line down for consistency, plus cx squared e to the x. Now all of that, don't forget, is equal to e to the x. Then now we're going to get well, cx squared e to the x minus cx squared e to the x plus cx squared e to the x, they all cancel out these terms, so you cross those out, and then we're going to get the following here: cx e to the x minus 4cx e to the x, they cancel out. So what we end up with is 2c e to the x is equal to e to the x. 2c equals 1, therefore c is going to be a half. So therefore we could write our particular integral as pi is y equals cx squared e to the x, meaning that our particular integral pi is a half x squared e to the x. And then what we can do now is to write our general solution as y equals the complementary function plus pi. So that gives me the following here. I get a plus bx e to the x plus a half x squared e to the x. And that's the solution for our differential equation.